This is the second video in a two-part video series covering U-substitution, the method for integrating and undoing the chain rule for derivatives. In this particular video, there are no real concepts that we'll be teaching and nothing of the lecture or theorem type. All we're going to do are work some problems. There are times when the choice of U or the substitutions that have to be made for different parts of the integrand are trickier than normal. I've isolated some examples for you so that we can work through these so that you'll feel more comfortable when doing the homework. Let's take a look at the first example. When you have sine or cosine by itself raised to even powers, consider switching to the double angle formula from trig. I put the two double angle formulas that you most likely will want to use here onto the screen. Let's work through example 1, which is the indefinite integral sine squared of x dx. The indefinite integral means we will need to switch from the variable x to the variable u, find the antiderivative, then back out of u and get right back to x again. Let's get started. In order to write this one, since I have sine squared of x, then I know that I can rewrite this instead using the formula that I see here to replace sine squared. This lets me write the indefinite integral of 1 minus the cosine of 2x divided by 2 with the differential dx. Now, you can start to take some shortcuts if you feel like it. For example, if you look at this formula, you know that the 2 in the denominator is in fact a constant factor of 1/2. You could pull that out from the very beginning if you want. And that will leave 1 minus the cosine of 2x inside as the integrand with the differential dx. Now, the next part is to split this into two integrals. I don't want to do a u substitution here, since my u would have to be 1 minus cosine of 2x, and the derivative of a negative cosine would be a sine, but I don't have a sine. So instead, what I'll try is splitting it into two integrals. The integral of 1/2 1 dx minus 1/2 the integral of cosine of 2x dx. This is a very typical thing to see when you get into Calculus 2. What we have here is a mixture of different techniques of integration. For the first integral, I need nothing other than just the antiderivative of 1, which is x. Yay, I'm done, plus the constant of integration. The second part, however, does require u substitution because the argument to the trig function cosine is not x by itself. Thus, I need to write this as a u substitution where u becomes the argument 2x, which makes du be 2 dx. I don't have the 2, so I'll isolate the differential dx and substitute for it with du divided by 2. This will then let me write the next integral as minus 1/2, which is that 1/2, times the integral of the cosine of u, and to replace the dx, I'll do du divided by 2. The du will come to the back to be the bookend for the integral symbol, but the divided by 2 will go outside. That's a different divided by 2 from the one that was there originally. Make sure that you don't let one substitute for both. Now what will I need to do? The next step, of course, is just to simplify and to do the indefinite integral. I have a 1/2 x from the first, tucking into the back of my head that, yes, I need a plus c somewhere at the end. The indefinite integral of cosine of u du would have to be sine of u du. So I get sine of u with a plus constant at the end. Now I've got to get out of that u and back to the original, which gives me 1/2 x minus 1/4 the sine of 2x plus a constant. That is an antiderivative function to the original integrand sine squared of x. Let's look at the next example. The next example involves, instead of sine squared, cosine squared. It also has, instead of a simple argument to the trig function, it has 8 theta as an argument to the trig function. And it's a definite integral. We could choose method 1 or we could choose method 2. You may do whichever you prefer. Let's see how it goes, and then maybe we'll do it both ways, and then we can decide at the end which one was easier. If we want to switch entirely over to U, that was what I was calling method 1 in the previous video. Switch to U completely. If I'm going to switch to U completely, then I know that I'll have to compute du and find the new limits of integration with respect to U and not with respect to theta. However, to do that, I need to use the double angle formula to get me out of cosine squared. How would I rewrite the integral from 0 to pi divided by 4 of the cosine squared of the argument 8 theta times d theta? Well, I would take this formula here that you see. I can pull the 1/2 that's in the denominator to the front as a constant factor. That still leaves the limits of integration from 0 to pi over 4. Now for the integrand, I have the numerator in parentheses, 1 plus the cosine of double what was there before. Remember when you apply the formula that you don't get 2 theta, you get double whatever was originally there. Since it was originally 8 theta, when I double that, I should get 16 theta. And then my differential is d theta. Now I split it into 2 definite integrals, one for each term. When I split it into each term, this will let me evaluate them separately. This gives me the integral of 1/2 from 0 to pi over, that should be 4, of 1 d theta plus 1/2 the integral from 0 to pi over 4 of the cosine of 16 theta d theta. The first one I can do using the antiderivative for 1, which will be theta, so that I get 1/2 theta evaluated between 0 and pi over 4. Remember, the definite integral should give you a definite number. You should get a finite real number, or you should get infinity, one or the other. Now, what I'm going to have for the second one is, notice that it is, in fact, U substitution. Now, what I need to do is find U. If I'm going to let U be the argument to the trig function, that would be 16 theta. That makes du 16 d theta. If I want to do method 1, I need to change the limits of integration from theta values to u values. So then I write, when theta equals 0, u equals, well, let's see, 16 times 0 would be 0. Okay, when theta is pi over 4, 16 times pi over 4 would give me 4 pi. Those will replace the limits of integration and allow them to reflect the new differential du. This becomes 1/2 the integral from 0 to 4 pi of the cosine of u du. However, notice here that I have not yet solved for what's present. What was present was d theta. I don't have the 16. This means that d theta is du divided by 16. That means I also need a 1 over 16 on the outside of the integral. Now, remember that when you switch like this and you change your limits of integration, even if it ends up the same number, it doesn't represent the same thing. This one is an x equals 0. This one is a u equals 0. They're not identical. Now let's move on to the next part. Now let's evaluate the first integral that we have by plugging in the limits of integration. Leave the 1/2 out as a common factor. This gives me pi over 4 minus 0, which is pi over 4, and half of pi over 4 is pi over 8. For the second part, 1/2 times 1/16 gives me 1 over 32. The antiderivative of cosine is sine. This will give me the sine of u evaluated between u equals 0 and u equals 4 pi. Now I can plug those in and leave the 1 over 32 outside as a common factor. I have the sine of 4 pi minus the sine of 0. However, I know that the sine of 4 pi is 0, and so is the sine of 0. That means that my final solution for this one is just pi over 8. Let's rework the same problem, but let's use method 2. Here is example 2 again. Remember that both methods start out the same way. I need to replace the cosine squared with the double angle formula. This lets me write the integral from 0 to pi over 4 of, pull the 1/2 that was in the denominator to the front, and then write the numerator as the new integrand. 1 plus the cosine of double what was there before, which will give us 16 theta. Now I'll split it into two integrals. 1/2 the definite integral from 0 to pi over 4 of 1 d theta. This part does not change since it is not a part of the u substitution. To save time, we'll just simply write down what we got, which was pi over 8. Dot, 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 pi over 8. What about the second term? We split that off as a separate integral, 1/2 times the integral from 0 to pi over 4 of the cosine of 16 theta d theta. Notice there is supposed to be a slight bit of distance between the integrand and the differential. I've exaggerated it here, but if you look at it in a textbook, you'll notice that the spacing is just ever so slightly larger than it normally is between two characters. I am going to do u substitution again, but I'm not going to replace the limits of integration. In this case, I simply write again that I have u equal to 16 theta and du equal to 16 d theta. Since I don't have the 16, I solve for the differential d theta to get du divided by 16. This will bring a factor of 1/16 to join the factor of 1/2 before the integral. I'm now going to have to write that theta equals 0 to theta equals pi over 4, since my new differential will be du. And I have cosine of u du. I know the antiderivative is sine of u. That is going to let me write, continuing down each piece, 1 over 32, the sine of u evaluated between theta equals 0 and theta equals pi over 4. Now I need to get out of u and get back to x, or in this case, theta. U is 16 theta. That lets me write pi over 8 plus 1 over 32 times the sine of 16 theta, and now I can drop the theta equals and simply write 0 to pi over 4. Now I'll plug in those values. Pi over 8 still hanging out, so is the 1 over 32, and now I plug in place of theta, pi over 4. This gives me 16 times pi over 4, which leads to 4 pi. Same thing I got earlier, minus the sine of 16 times 0, which is, of course, 0. Same thing I got earlier. This is always going to happen. This is, in fact, where those numbers came from. So now I can evaluate what those become. The sine of 4 pi is 0, and the sine of 0 is 0. And that lets me write then that I get pi divided by 8 for the final amount of area. Let's take a look at our next example. In our next tricky example, I've got several things going on. I have a monomial factor x by itself, multiplied by cosine, which is being squared, meaning I have a composed function, which definitely makes me think use substitution. And I have inside the cosine another polynomial expression, x squared. That means that the second factor, cosine squared of x squared, is layered 3 deep. In other words, if I were to write it over here to the side, I've got on the outside something squared. What's squared? A cosine. A cosine of what? Of x squared. X squared is the inside of cosine, and cosine x squared is the inside of the squared power. Now, we don't deal with cosine squared as u unless we also have a sine. We don't have sine present in the integrand. That means I have no choice. I've got to use this double angle formula that you see here. This would be the same whether we used method 1 or method 2. I have cosine or sine to an even power, but not the other. Sometimes we have both sine and cosine to even powers, in which case we have to convert them both and then multiply out and keep going. Like I said, you'll spend one entire section on tricky trig integration when you get to Calculus 2. Let's take a look at what this one should become. The monomial factor x stays. I'm going to replace the cosine squared with what I have here. The 1/2 in the denominator is going to come outside as a factor of 1/2. Then I'm going to write the rest of the numerator as part of the integrand as another factor. In parentheses, 1 plus cosine. Now I need to double what was originally inside cosine. Originally inside cosine was x squared. That means I get 2x squared. Yes, I said it would be tricky, and it is. Double that x squared to get 2x squared. Don't square it. It's times 2. Then I have the differential dx. Now when I look at this, I have to pick a u. Now, before I pick the u, remember that we want to split it up if we can. We only use u substitution when we can't find a direct antiderivative. You always look for the easy way out first. So we'll split it up. 1/2 distributing the x times the 1 gives me 1/2 the integral of x dx. Then I distribute over the cosine. That gives me 1/2 the integral of x times the cosine of the quantity 2x squared with the differential dx. Now what do? Well, can you integrate the first integral without u substitution? Yes, of course. The antiderivative of x is x squared over 2, so we do it. 1/2 from the first factor times x squared divided by 2. I will eventually at some point need a plus c. You may want to add it at some step so you don't forget it. What about this second one? In this second one, I've got several different factors. I've got the 1/2 on the outside, which doesn't really contribute to anything. I've got the monomial x, which is probably a part of the differential du. And I've got a cosine composed with 2x squared. The only thing that's composed is the cosine and the 2x squared. That makes my best choice of u to be the inside 2x squared. Let's give it a shot. If I let u be 2x squared, then my du would be 4x dx. I don't have a 4. I do have an x dx, which is right there. That lets me solve for what is present, which is x dx. That means that x dx must be equal to du divided by 4. Now I'll do my substitution and replace that part. I get a plus 1/2, which is this 1/2. When I substitute, the original x dx that's here ringed in red gets replaced with du over 4. That gives me another constant factor of 1/4 to join the 1/2 on the outside of the integral. The du will go to the back. The cosine of 2x squared stays as the integrand, but the 2x squared is substituted out in place of u. That leads to this integral you see here. The next step, of course, is to simplify the arithmetic and evaluate the indefinite integral of cosine of u du. This would lead me in the first integral to have 1/4 x squared. The constant at the front of the next would be 1/8. The indefinite integral of cosine of u is sine of u. And don't forget that you've got to have a plus c. I'm not done because I need to get back out of u and back to only x. I replace the u with 2x squared. And that gives me this as my final answer. 1/4 x squared plus 1/8 the sine of quantity 2x squared plus a constant. Let's take a look at a different example. Here's another tricky trig function integral for you. Again, you'll spend an entire section on these in calculus 2. And if you take me, I have a really long handout to help you figure out how to simplify them. Let's take a look at this and see if we can figure out, what's u? I clearly have a 4x, which has been composed with both tangent and secant. That would tend to make me think that maybe 4x is u, but then again, I've got tangent raised to the 10th power and secant raised to the 2nd power. That would make me think that tangent or secant should be u. In truth, there are going to be 2 u substitutions here. You're not going to get away with just one. The trick to unraveling this is to think now, since you've identified that 4x is inside and probably at some point will be a u substitution, you've got to deal with the fact that you have 2 different trig functions. When you have 2 involved, try to think in terms of, well, which one's the derivative of the other? In this case, the derivative of tangent is secant squared. Not just one secant, but secant squared. My first choice for u is tangent of 4x. Let's write that down. U equals the tangent of 4x. Now, why did I choose tangent of 4x? Because the derivative of tangent is secant squared. Now I can take the derivative and abuse the notation by swinging the differential dx around. However, to take the derivative of tangent of 4x, don't forget you've got to do the chain rule and take the derivative of the inside. That gives me secant squared of 4x times the derivative of the inside, which is another 4. That would let me write it as 4 secant squared of 4x times the differential dx. Now let's look at our original integrand and identify what's already there and what's not. I already have secant squared of 4x dx. Here, I can isolate that part. I'm missing the common factor of 4. That means that I can divide both sides by 4 so that I can isolate the part of the integrand that is already a part of du, which is secant squared of 4x dx. When I substitute, I'll replace the secant squared of 4x times dx with du divided by 4. The 4 that's being divided will move to the outside as a factor of 1/4. That will leave the du at the back as a bookend for the other end of the integration symbol. Remember, you can't have an integral symbol without the differential. You have one, you have the other. Now I need to replace the tangent. In this case, u is tangent of 4x, and it's being raised to the 10th power. You may want to write this as u to the 10th. This then just became a very simple power function. The derivative, or antiderivative rather, will be u to the 11th divided by 11 plus a constant. Quite simple. Remember that since the 1/4 and the 11 are both in the denominator, this will actually give me 1/44, and I can replace u with the tangent of 4x again, raised to the 11th power. You can either put the tangent of 4x in parentheses with the 11th power outside, or you can place the 11th power between the tan symbol and the parentheses around the 4x. This one looked quite complicated, but ended up not being too bad, provided we chose the right u. Don't go too deep when you're trying to find u. You typically only go one layer down. If you need to go more than that, you may have to do u substitution more than once, but that's okay. I think example 5 is probably one of the trickiest u substitution integration problems you'll see. It looks deceptively simple. The difficult part is knowing that there is something hiding in there. The problem here is that until you've been shown how to do one of these, it may never occur to you without weeks and weeks of contemplation. Keep in mind that the people who discovered these methods did not sit down and write these out in one day or a week, and sometimes not a month or even a year. They worked on these problems over long periods of time with their friends who gave them advice, helped them, pointed out their errors, the same way you're learning it. Let's look at this one and see what's so tricky about this one. When I look at example 5, I see first that it is a fraction, which tends to make me want to look at the denominator. In this case, the denominator is more complicated, which really does lead me to believe that it's got to be the denominator. However, the denominator also has a radical, and I know that under a radical is a good place to find u. Wow, this is looking kind of crazy. It looks to me like maybe I could let u be x minus 4. Let's give it a shot and see what happens. If I choose u to be the radicand, the part that's under the radical but doesn't include the radical, then I can find du by taking the derivative with respect to x. This would just give me a 1, and when I swing the differential around to the other side, I get du equals dx. Yay! So far, so good. Here's the tricky part. Now when you try to rewrite it, you will have the square root of u in place of the square root of x minus 4. The dx gets replaced with du, and now you're stuck, because in the numerator, you still have this monomial factor of x. It is not written in terms of u. What to do? You cannot integrate with the x there. It is dependent on u, and u is dependent on x. They are related. Well, then let's use that. Let's use this relationship we have up here for what u is to find out what x is. I can do that. If u equals x minus 4, then x must be u plus 4. Haha, very tricky. Not something that most people would think to do their first time out, or second, or 10th, and maybe not your 50th. We're going to replace x then with u plus 4. This gives me u plus 4 divided by the square root of u du. Now you may look at this and go, great, but I can't integrate that either. Yes, you can. Remember, when you have a monomial denominator, that you can divide each term in the numerator by the monomial single term denominator. In other words, I can rewrite this as u over the square root of u plus 4 over the square root of u, all integrated with respect to u. Now I can write the square root of u in its power form. In its power form, this would be the integral of u divided by u to the 1/2 du plus, splitting it into two integrals, 4 times the integral of u to the negative 1/2 du. In the next step, notice that on the left, these are being divided, but they have the same base u. The power on the u in the numerator is not written, but it is a 1. And the rule for exponents is when the bases are the same and you're dividing, subtract the denominator power from the numerator power. That gives me 1 minus 1/2, or the integral of u to the 1/2 du. The next one I can already integrate using the power rule for integrals. Add 1 to your negative 1/2, and that will give you u to the positive 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal 2 over 1. These are both indefinite integrals, so you might as well tack on the plus c before you forget it. In the next step, the integral of u to the 1/2 by the power rule for integrals gives me u to the 3/2 times 2/3, and then I have a plus 8 u to the 1/2 plus c. I got to get out of u and get back to x. U was x plus, or rather x minus 4. That gives me 2/3 times x minus 4 to the 3/2 plus 8 times x minus 4 to the 1/2 plus the constant of integration. Remember that the 1/2 power is the square root, so it would be equivalent to write it in the following form, though it's not required and I wouldn't necessarily expect this. You could, however, write it this way, and there might be occasions where it would make more sense to write it that way. I leave it to your discretion. Let's take a look at the next tricky integral. In the next tricky integral, you'll notice that I've switched out of x and I've made it a y. For some reason, this always distresses students and really freaks them out. I have to admit, it does kind of give me a funny feeling in my stomach too. It just doesn't look right. However, what are we going to find for u? What do you think? What's your best guess? Where would you look for u? Probably in the denominator. Look for the more complicated part. Look for a composed function. Look for something inside something else. Yep, there it is. That y plus 1 is inside the 4th power, and it's in the denominator. Double win. It's got to be u equals y plus 1. When I compute du, I am taking the derivative with respect to y. Keep that in mind. That gives me 1, and abusing the notation leads me to write that du equals dy. Now when I substitute, remember that this part became the u, so I have u to the 4th in the denominator. Then I have dy replaced with du. The problem is the y squared. But we can do a similar thing to what we did last time, which is take what's up here at the top in our expression for u and solve it for y instead. If u equals y plus 1, then y must equal u minus 1. Great, but that's not what's in the numerator. That's a y squared. No problem. If y is u minus 1, then y squared must be u minus 1 quantity squared. Now, I can replace that here in the integral. Now, of course, I'm going to need to multiply out the u minus 1 quantity squared. Because both the numerator and denominator are written in terms of u, and the denominator is a monomial, single term. That means when I multiply out the numerator, I can divide each term in the numerator by the denominator and split up the radicals. Let's finish it out doing that now. This then leads to the integral. Multiplying out the binomial would give me u squared minus 2u plus 1 all over u to the 4th du. Yes, it's tricky, but it's doable. Separating these into different integrals, or just separating them into different terms, would lead u to the negative 2, since power 2 minus power 4 gives you power negative 2 when written in the numerator, minus 2u to the negative 3, since the understood power 1 minus power 4 gives me a negative 3, plus u to the negative 4. Again, this is an understood u to the 0, and 0 minus 4 is negative 4. The differential remains du. What is my next step going to look like? In my next step, I should integrate each individual term by finding the antiderivative. The antiderivative of u to the negative 2 is u to the negative 1 divided by negative 1. For the next term, I have negative 2 times the antiderivative u to the negative 2 divided by negative 2. For the last term, I have the antiderivative u to the negative 3 divided by negative 3. Don't forget the constant of integration. In my Calculus 2 classes and most of my Calculus 1, I take off 3 out of 10 points for getting plus c or the differential. That is a whopping lot of points. You can't afford it, so don't forget it. In the next term, I'll rewrite it as negative 1 over u. The negative 2's cancel, and I get plus 1 over u squared. And for the third term, I get minus 1/3 or 1 over 3 u cubed, plus the constant. Now we need to replace u with what we set it equal to, y plus 1. When we replace it with y plus 1, we get negative 1 over y plus 1 plus 1 over y plus 1 quantity squared minus 1 over 3 quantity y plus 1 cubed plus c. No, I would not multiply these out. The higher you go in mathematics, the less likely you are to multiply them out completely and write them in descending order. We like instead to leave it where the structure of what's happening and how the terms are related is more clear. Leaving it in this form makes it obvious to anybody looking that these denominators all have the factor y plus 1. If you multiply them out, you'll lose that information. So it's much better to leave them as they are here. We're now ready for example 7. In example 7, we have a binomial multiplied by a radical. Under the radical, we have a linear polynomial. Notice that our integral is written in terms of the independent variable z, as in zebra. In this case, what we can do is to look for u in the most complicated factor, which is the radical. Probably we should let it be the radicand itself. Let's let u be equal to 3z plus 2. I know my z's and 2's look identical. However, it's a z if it has the vertical part in the middle. Otherwise, it's a 2. What is the differential du? That would be the derivative, which would give me a 3 with a dz on the end. Once we have that, however, we would be a little bit puzzled looking at what's still here. Up here, I have a z plus 1, which does not relate to 3z plus 2. So what am I going to do? How can I deal with this? This is a different way of solving a problem and something that you maybe have not encountered very often before. I wouldn't say that it is a common technique, but it's definitely not uncommon. We use the technique of multiplying by a form of 1 a lot. This is the other technique, which I will call add 0. We don't use it as often, but there are occasions where really nothing else will work. The problem is, I need to represent the z plus 1, which is remaining here in the integrand, somehow in terms of u. But my u is 3z plus 2, and there is nothing I can factor out here that will turn it into a z plus 1. I know that so far all I can write is the integral of z plus 1 times the square root of u. I could solve for dz by dividing both sides by 3, and that would give me that dz is du divided by 3. That will put the 1/3 on the front and the dz at the back. Oops, not the dz, the du at the back. The problem is I still have this z. This is the trick called add 0. Let's take a look at it over here on the right side. What do I mean by add 0? I mean exactly that. If I add 0 to anything, I haven't changed it. However, there's more than one way to write 0, just as there's more than one way to write the number 1. I can write 2 divided by 2 for 1, or 1 over x divided by 1 over x, or x over x. All of those represent the number 1. In this case, I need to write it in such a way that I can get something out of it so that I can factor this 3 off and be left with a z plus 1. In other words, I'm hoping I can get a 3z plus 3 because I know that I could then factor off the 3 and get a z plus 1. But I don't have 3z plus 3. I have 3z plus 2. If I have 3z plus 2, how could I add 0 to get a 3z plus 3? Well, I need another 1. So add your 1 and subtract your 1. 1 minus 1 is another way to write 0. We call this adding 0. This will let me write the first part as 3z plus 3 with the minus 1 tacked onto it. Let's see how this trick will let us finish solving this integral that we have here. If I get to here, how can I use this now to replace the u and the z plus 1? Think back to where the 3 times the parentheses z plus 1 minus 1 came from. This is really 3z plus 2. Adding 1 and subtracting 1 is adding 0, which is nothing, which means it's still u. This thing that you see here is u. Now that I have this written as equal to u, can I solve this equation for what's in the parentheses, for the z plus 1? Of course I can. First, I'm going to add the 1 to both sides to get 3 times z plus 1 in parentheses equal to u plus 1. Now to isolate z plus 1, I need to divide by 3. That will let me then write the next thing, which will be that z plus 1 in parentheses is equal to 1/3 in parentheses u plus 1. Or you could write it as u plus 1 divided by 3, whichever you prefer. Let's substitute it now into our indefinite integral. The 1/3 factor on the front is still there. Instead of writing z plus 1, I'm going to substitute another constant 1/3 factor and u plus 1. The extra 1/3 factor is a constant that can be brought out of the integral, but the u plus 1 cannot because it depends on the differential, which is du. Then I have the square root of u. Now can I rewrite this? What can I write for it now? In the next step, what I need to do is distribute the square root of u over the binomial factor u plus 1. I can think of the u, instead of u to the square root, I can think of it as u to the 1/2 power. Then, since the bases are both u, I can add their powers. This leads to 1/9 times the integral of u to the 1 plus 1/2 gives me 3/2 power plus u to the 1/2 power du. In the next step, I find the antiderivative for each term. That would give me u to the 5/2 times the reciprocal 2/5 plus also a 1/9 factor, since it's distributed over all the terms inside the integrand, and the antiderivative u to the 3/2 times the reciprocal 2/3. Don't forget the constant of integration plus c. Then this leads to 2 divided by 45, and if I want, I can replace the u's right here and now. U is 3z plus 2. This would give me 3z plus 2 raised to the 5/2 power plus 2 over 27 times 3z plus 2 raised to the 3/2 power plus the constant of integration. This is a very difficult problem for U substitution, and I've seen Calculus 2 students scratching their heads over it. If you struggle with this one, don't worry. Now that you've seen it once, you may be able to come up with it again after some struggle and trying again and again. Let's now focus on example 8. In example 8, we have what looks like a rational function but is not, because it is not the ratio of two polynomials. It is a fraction, but it's a fraction with division of two exponential functions. However, the exponentials e to the x and the exponential e to the 2x never ever hit the x-axis or go negative, which means that there is no value that I have to throw out of the domain. There's no way to make that denominator 0. They're defined for all real numbers. What do you suppose I should use for u? In this particular problem, it is not as clear what might be u. Let's see what we can come up with. My first thought is, since the denominator is more complicated, let's try that for u. In that case, I would write u equals e to the 2x power plus 1. To find the derivative with respect to x, I would get another e to the 2x plus, or not plus, but times the derivative of the inside function 2x, which is 2. Remember that the derivative of the constant 1 is 0. This would also give me the differential dx swung around to the right side. Now, the problem is I don't have that. What I have is e to the x dx, the single x, not a 2x. How am I going to handle that? There are a couple of ways of handling it. There is a way to back your way into finding the solution from this form. However, it is probably not the easiest way to do it. In this case, an easier way might be to go through and maybe allow e to the x instead to be our u. Again, it can be done either way, but for most students, when they reach this point, they're kind of stumped. Yes, there's a tricky algebra technique that you can use to get there, but for most students, the easier path is to back up and go, well, that didn't seem to work. Let me try e to the x. Why e to the x? Well, because I have e to the x in the numerator, and I have e to the 2x in the denominator. If I have e to the 2x, it means it's actually e to the x quantity squared. Since you have one base and two powers, you multiply the powers. If I let u be e to the x, then du would be also e to the x dx. Now, what was I saying about the e to the x squared? Think of it this way. If I write e to the x and I square it, I have one base, which is e, and it has two powers, x and 2. The rule is multiply the powers. That gives me e to the 2x. If I let u be e to the x, then I can think of e to the 2x as u squared. What does that let me write? If I'm looking at this one, this would then lead to the following. I would have, what would I have? I would have e to the x in the numerator, dx in the denominator, and I would have u squared plus 1. Now, e to the x dx is in fact part of du, the whole of du. So I could replace that part with du. This would give me 1 over u squared plus 1 du. Now, you may not remember this one, but it should be ringing a faint bell. You may or may not have covered these yet. If you haven't covered them yet, come back to this one later in a few more days after you've looked at inverse trig integrals, because that's what you have. This is arctangent of u. When I'm looking at this, remember that when you take the derivative of arctangent, you get 1 over 1 plus u squared, and that's what I have. So this must be, in fact, the arctangent of u. In other words, for those of you who like it in the other form, this is the inverse tangent function of u plus the constant c. And then I would replace the u with e to the x. I prefer the arctangent form because it never lets me forget that this is not tangent, and it's definitely not the reciprocal. This is the angle, beginning with a, whose tangent gives me e to the x. This is a very tricky one. If you struggle with this one, again, don't panic. You'll be doing a lot of these when you get to Calculus 2. It is a major integration technique, but this is not something I focus much on in Calculus 1. I show it to you here because I want you to have seen it, but I'm not going to test you on this one. Let's take a look at another tricky one. Our next tricky u substitution has natural log in it. Lots of students do not like natural log, and they get that sort of sick feeling in their stomach when it pops up. You need to get over it because it's a pretty major function. It comes up a lot in the real world, and by a lot, I mean a lot. Get used to it. It's not going away. When we look at this one, we need to find a good choice of u. I will tell you that natural log is sort of a difficult function to deal with. It's kind of the bully on the block. It gets to be u. It's always u. If it's there, it's usually u. So my first thing is to let natural log be u. In this case, I'm going to write u equals natural log of x. Even though it's in the numerator, the fact that it's natural log and that the argument is too simple to be u lets me think that probably u is the natural log itself. What's the derivative of natural log? Yep, that's 1 over the argument, and then we swing the differential around. That's an even bigger reason to suspect that u is natural log of x if you have 1 over x present in the integrand. That means that I can now rewrite the definite integral. However, I've got to make a choice. Am I going to do method 1 or method 2? Are we getting rid of x forever and ever, or are we coming back to it? This time, let's do method 1 and get rid of it forever and ever. When x equals 1, what's u? With natural log and other complicated functions, I recommend you just go ahead and write it down. Don't try to do it in your head. That's when you make careless mistakes. Just write it down. When x equals e squared, and yes, that's e squared, then u would be the natural log of e squared. But natural log and the exponential are inverse operations, and this will just give me 2. Now that I have them, I can replace them, but be sure you replace them in the exact order they were produced. I replace the 1 with the 0 and e squared with 2. This lets me rewrite the definite integral in terms of u only, from 0 to 2 of, well, u du. That's it. What could be easier? This just gives me u squared over 2 evaluated between 0 and 2. Now we plug in the limits of integration. I'm going to pull the 1/2 out because I don't want to deal with a fraction more than once. That leaves u squared to be evaluated between 0 and 2, which gives me 1/2 times, well, u squared would be 2 squared minus 0 squared, but, well, 0 squared is 0. So that's just going to lead me to 1/2 of 4. Oops, I'm thinking and writing at the same time, which doesn't always work out well. 1/2 of 4, which gives me 2. And that's my final answer. Not as bad as it might have appeared at first. Let's move on to another tricky one. In 9, we again have 2 different polynomial expressions. This one, however, is a definite integral. Let's run through it relatively quickly. Identify your u as the more complicated binomial being raised to the 7th power. Now find the differential du, taking the derivative, to get 2x minus 2. Put it in parentheses and multiply by the swung around differential dx. This is not exactly what I still have remaining in the integral. This part becomes u to the 7th, but this is x minus 1. But I can rewrite this as 2 times x minus 1 dx. Now I can isolate what is already present in the integrand that doesn't become a part of u. I have the dx and the x minus 1. That then will let me rewrite it in the next way. This time we'll use method 2. We'll substitute to u and substitute back. This gives me that du over 2 is equal to x minus 1 in parentheses times dx. That gives me the definite integral from x equal -1 to x equal 1. Note I must write the x equal since the differential will now be u to the 7th du. And I've got a factor of 1/2, which needs to be brought to the front. The antiderivative to u to the 7th is u to the 8th divided by 8. I need to evaluate between x equal -1 and x equal 1. Switching back now into the x form, I have that u is x squared minus 2x, which needs to be evaluated between -1 and 1. Leave the 1/16 outside. It'll just complicate your life if you drag it in there. That will leave you 1 squared minus 2 times 1 minus, now let's do the negative part, maybe in a different color and with parentheses around it. -1 squared minus 2 times -1. Simplifying this leads to the following. I get 1 squared minus 2, which will give me a -1. In the parentheses, -1 squared is 1, and -2 times -1 is +2. That gives me 3, but it's -3. So I have -1 minus 3, which gives me -4. 1/16 times -4 gives me a -1/4 for my final value of the definite integral. Let's move to our next tricky integral. For this one, you'll notice that I have several layers of composition. I have sine squared substituted for the power on an exponential. The sine is being squared, which means sine is nested inside of a second power. I also have a 2x inside of a sine factor that is outside and not a part of the exponential factor. Yuck! For this one, you need a different trig identity, also called a double angle identity or half angle, depending on which way you want to go, which is the sine of 2 theta is 2 sine theta cosine theta. I will say that I use this one quite a bit. I won't say that I use it all the time, but it's pretty common. It's common enough that I have memorized it just out of habit over the years. Now let's figure out what would be a good choice for you. The most complicated part of this whole thing is the exponential. And the exponential has a power, and the power is the right place to find u. In this case, it looks to me like maybe u should be the entire power. Remember, don't dive too deep in looking for u. Don't go to the innermost function, go down one layer. That means I'm going to make u be sine squared of x. The derivative will then involve chain rule. 2 sine x times derivative of sine is cosine x. Haha, do you see what I see? Yeah, that is in fact that identity that I have up here. If the derivative is 2 sine x cosine x, I can replace that then with the sine of 2x. Don't forget to swing your differential around to the other side. That means I can replace the 2 sine x cosine x with, instead, the sine of 2x. Or I can leave it the way it is here, whichever you prefer. This, of course, gives me the same thing. Now that I'm looking at it, what do I have? Well, I have that. That part becomes du. The other part becomes e to the u. Now on this one, let's go ahead and switch our limits of integration. When x equals 0, what's u? Well, if x is 0, the sine of 0 is 0, and 0 squared is still 0. What about when x is equal to pi divided by 4? For this one, you probably should write it down. U would be the sine of pi divided by 4 quantity squared. Remember that pi divided by 4 is a reference angle of 45 degrees, And that means that I get the square root of 2 divided by 2. When I square it, I get 2 over 4, which is 1/2. That's a terrible 2. Let me rewrite that. Okay, moving on then, I can now rewrite the integral in terms of only u. This will take it from u equal to 0 to u equal 1/2. And I will write e to the u du. Well, nothing can be easier than e to the u. That's just e to the u. And it's evaluated between 0 and 1/2. The difference between the methods is, do you want to do your work in changing the limits of integration, or do your work on the back end when you plug in the limits of integration? You're going to do the work one way or the other. In this case, I get left with e to the 1/2 minus e to the 0. E to the 0 is 1. Let's take a look at our next tricky integral. For this one, I want you to take a moment, copy down the problem, then pause the video, work the problem yourself, then turn it back on and compare your answer to mine. For this particular problem, it is a mixture of both sine and cosine. However, cosine's in the denominator and it's being squared. That makes cosine the correct choice for you. Plus, sine is the derivative of cosine if you put a negative on it. Let's take a look at the solution. Rather than go through and explain it step by step, I'll instead give you a few minutes to pause the video on each section so that you can follow it all the way down and make sure you've solved it correctly. Here's the first part using either method. And here's the second part. Notice that we got the same solution using either method, but again, it does appear that method 1 is somewhat shorter. However, the work is being done in converting the limits of integration. Again, it is just a matter of preference and sometimes the particular function involved to tell you which is the better choice. We have one last example to look at, and we'll do it the way we did the last one. I'll let you look at it, pause the video, work it on your own, and then I'll show you my solutions. Here's example 13, our last example. Take a moment to copy this down, then pause the video and solve it on your own. You can choose either method 1 or method 2. When looking at this problem, again, we have a mixture of different types of functions. The polynomial x squared, which is a monomial factor. The cubic x cubed plus 1, which is the power on an exponential function. The x cubed plus 1 is composed inside the exponential, making it the best choice of u. That gives us du as 3x squared dx, but we only have x squared dx, so we have to divide by 3. I will pause it here so that you can have a chance to look at the two methods and see how far you manage to get without making any mistakes. Let's scroll down to the next section. And the last. Hopefully, after watching these two videos, you'll feel more confident about doing a U substitution integration problem. I hope that you become masters of these because they truly are fundamental to doing integration from this point forward. There's almost nothing that you can do in Calculus 2 if you cannot do accurate U substitution every time you see it. It really is that basic. This is the end of this video.